All right. Okay, so yeah, thank you so much for being here. So this is the first part of a two-part seminar. Right. So the first part, I'm going to tell you a bit the story of this problem, why it became so famous in the community, and the motivation, which is at least twofold, if not threefold. And so in the second part tomorrow, we're going to look at some proof ideas, because that's also an interesting part, although a bit more technical. But today it's not. It's so hopefully a bit more introductory. Okay, and to tell you the story, I need to start with something on the board that I don't have in the slides, namely something called quantum hypothesis testing. Okay, so what's quantum hypothesis testing? Well, it's the art of discriminating quantum states. Right, so let's say that in the simplest possible setting, let's say that you have two states, rho and sigma, and you hide one of them in a box, and you don't tell the adversary which states you have hidden in the box. And now the adversary has to, or us, if you want, we have to perform a measurement to guess which state we got, right? So this will be a classical measurement, and then we will guess rho or guess sigma. So this is a measurement, so it's a binary P of M, right? Because in the end, we are interested in two outcomes, rho or sigma. So we can model it as in quantum mechanics as a P of M with binary outcome like this. And T, of course, will be a generic test. So T is some operator between 0 and the identity. Very good. So why is this task relevant or interesting? Well, okay, for clear operational reasons. I mean, it has a clear interpretation. Like, for example, if you want to do device certification, you bought a device that corresponds to you, it produces a good state rho with some good properties, but you don't trust the company. You want to test the device yourself, and you suspect that it produces some rubbish state sigma, and you want to ascertain whether this is the case or not. That's a task to do it. Okay, but this is kind of a practical reason, but there's also a more fundamental reason, which is that a lot of times in quantum channel theory, we want to do, we have some quantum objects that are noisy in some sense. This might be states or channels or something, and we want to purify them. We want to distill the resource that they contain and remove the noise. And distillation, in this vague sense, is, well, it's a discrimination procedure, because it discriminates the objects that have resource from the objects that don't have resource. The objects that have resource will produce pure resource, and the objects that don't have resource will produce zero resource. So any purification or distillation task in this general sense amounts to state discrimination, well, or a hypothesis testing task more generally. And therefore, you can use hypothesis testing to place bounds on how well you can perform this purification tasks or distillation tasks. Okay, so that's kind of the fundamental reason why this this task and all of the quantities that helps defining pop out everywhere in quantum channel theory somehow. Okay, well, okay, so there are two types of errors, right? In the setting, so there is something called the type 1 error, which is, of course, it's when the state was, so the state was rho, but we guessed sigma. Okay, so and the type 2 error, right, when the state was sigma, but we guessed rho, and the opposite. Okay, so what are the corresponding error probabilities? Well, the probability of type 1 error, type 1, which is usually denoted like alpha of t. T because it depends on the test, of course. It also depends on the states, but let me not write that. That's simply, you see that the probability that the state was rho, so we do trace of rho against, well, identity minus t, the probability of guessing sigma. Okay, and vice versa, here the probability of type 2, beta of t, let's just trace sigma t. Okay, so these two errors, they are not in general equally consequential, okay? For reasons that we all have learned during the pandemic, for example, like false positives and false negatives, they're just not the same. And for example, in the setting before, it might be way more serious to believe that your device is good when it's not. Maybe it's maliciously engineered or something, and vice versa. Okay, so what we really care about is, let's say the type 2 error program. I mean, everything is symmetric in this setting. Of course, can swap rho and sigma, but let's say that sigma is the noisy state. It's kind of the no resource state, and so we want to minimize the type 2 error probability. So probability we believe that the state was good when it's in fact it's not. So people usually define something called beta epsilon or sigma, and that's simply the minimum type 2 error probability that's associated with any test, such that the type 1 error probability is smaller than epsilon. Okay, so epsilon is some number between 0 and 1, some threshold that we fix for the type 1 error. Okay, and what we care about here is, in fact, the asymptotic limit, because in quantum channel theory, you always want to compute things asymptotically. Right? What does it mean, the asymptotic limit? Well, okay, so let's say that the device that produces states rho sigma, you can press a button. How many times do you need to press the button to discriminate the states up to a certain precision? And so what people want to study is this quantity. So beta epsilon of many copies of the state. So rho tensor n versus sigma tensor n. Okay, so it's just many copies of the state rho, many copies of the state sigma. What do we expect for this quantity? Well, we expect it to decay exponentially fast. And why is that? Well, because you have many trials, and whenever you have many trials, you want to decide it's increasingly less likely in an exponential way that a state like sigma can pass itself for rho, can fool you and make you believe that it's rho. And this would be in an exponential way, right? So we believe that this will decay exponentially. Now let me write this: x of minus cn. So the task now is compute c. Okay, to do that, it's very useful to define a quantity called the hypothesis testing relative entropy. Hypothesis testing relative entropy of two states. We place ourselves already in the situation where we want to extract the c. How do we do this? Well, we take minus log. Because we want to divide by n in. So let me define this as minus log of beta epsilon rho sigma. This is called hypothesis testing relative entropy. And this is really type 2 error probability, right? But in disguise with minus log. So that's why some people don't like to write hypothesis testing relative entropy. They just write minus log beta epsilon. Okay, so now let's see. Let's see, which is called the Stein exponent between rho and sigma. That's simply given by, we can define it if you want, or it's given by, well, okay. So, yeah, the lim-inf, let's say the lim-inf. I mean, here there are several caveats. Let's say that we define it like this. We want to compute the hypothesis testing relative entropy for n states, for n copies of the states, rho tensor n and sigma tensor n, and we divide by n. Okay. And okay, I'm taking the lim-inf because I want to consider the worst case scenario. And okay, formally this quantity still depends on epsilon. And so if you want, you can take epsilon to 0 later. So this looks very cumbersome definition, but it turns out that the lim-inf is not needed. This quantity has a limit, and the limit is actually independent of epsilon. So all this precautions them taking, they're actually useless. But okay, to define the quantity formally in the first place, you better put them there. Okay, so that's a Stein exponent. Nice. And great. So let's gather some intuition. So let's look at a classical case. Okay. Now, maybe I should. What do I do? Okay. Let's look at the classical case. So what's a classical case? Well, you have a, like in Matthias's talk yesterday, you have a finite alphabet X. And you have P and Q probability distributions on X. Okay, so now like the n copy case means that we get a sequence, right? So we have a random variable if you want, and we don't know whether this comes from P or comes from Q, right? We want to decide between these two options. So what we're getting is a sequence of symbols, right? So something like this. Xn, so a bunch of symbols, right? And we want to decide whether they come from one probability distribution or the other. Okay, right, so there is a fundamental notion which is that of type of a sequence. So the type of the sequence Xn, which people call sometimes Txn, is a probability distribution. And it's defined, so it's a probability distribution on X, and it's the empirical probability distribution associated with that sequence. Okay. So if you want, like formally, the type of Xn on a symbol X is just the number of times that the symbol X appears in the sequence divided by n. It's really the empirical probability distribution associated with that. Okay. Nice. So there's something called the type class. So let's say that I take a type Ten, I don't know. And there's something called the type class, En, which is just a set of sequences with that type. Okay, the set of sequences with a given type, a given empirical probability distribution, so that they're basically all identical except for permutations. Okay. So that makes very easy the calculation of the size of this type class. In fact, Matthias did it yesterday. Essentially, well, he did it, right? So this is so if you want to compute the size of this, this is really like the multinomial, like n, and then n choose t of x, t of x1 and t of x2. Sorry, I mean t of the first symbol, let's say 1, t of the second symbol, let's say 2, and so on. And so if you approximate this with Stirling, and you can make this rigorous, like with upper and lower bounds, so they're very similar. This turns out to be, say, the exponential, whatever base you want, 2 or whatever, and then n times the entropy of the type. Okay, so what's the entropy of the type? Well, the entropy of the type, like the entropy of any probability distribution, is what Matthias defined yesterday. It's minus sum over the symbols px log x, log px. Okay, this is the quantity comes out from Stirling, right? Because Stirling is just n log n stuff, right? Remember, and there's this linear term that cancels out because normalization that also Matthias showed yesterday. Right. Okay, very good. So now with this kind of tools, we can come up with an easy test, right? So what would you do in practice if you see a sequence? You check whether it's typical for P, and if it's not typical for P, you declare it's Q. That's a very intuitive test. In fact, the test works. The test works because so let's do this intuitive and non-rigorous calculation to show that it does work. Okay, so right, so the test is basically check whether but essentially the type of the sequence that you get is close to P, and if yes, guess P, and otherwise guess Q. Okay, so so the type 1 error probability turns out to go to 0, and this is just the law of large numbers, right? By the law of large numbers, if the sequence comes from P, the type will be close to P, right? Up to any degree of precision, yes.
You're going to check that the sequences are close or that their entropys are close?
I'm just checking that the type is closed, so like the whole,
L1 distance?
for example, L1 distance, that's fine. That's called a strong typicality test, right? Yeah. Right. So the type 1 error probability, it turns out that the type, if I do this type 1 error probability, I don't know, alpha, let's call this alpha n of this test. It's very easy to see that this goes to 0. Okay, so what about the type 2 error probability? Okay, so let's try to approximate the type 2 error probability. The type 2 error probability is just let's do again an intuitive calculation, non-rigorous, but it can be made rigorous with very little effort. So that, well, it's going to be the sum over all sequences such that the type is not close to P. Sometimes, somehow, right? And here we have Qn or Q tensor n, call it the IID distribution induced by Q of the sequence. Now the big realization is that this one we can write like, okay, product over the symbols of Q of xi. But there's the product over the symbols goes from 1 to n, but there's a better way to reorganize this product, which is that of grouping together all the factors that belong to the same symbol x. So this we can rewrite like this. And so here we can write, well, let's say the exponential. Now, right, so you get log, so you will have a sum over x, right? Because it will be a product over the symbols. And how many times? So here we've got log qx. But how many times does q of x appear for a given symbol? Well, just the number of times that the symbol appears in the sequence. So that's also n txn of x. Oh, I made a mistake, of course. So this is the number of, so the error happens when you guess, so when the sequence is actually type close to P. Right, so this is actually when the type is close to P. The type 2 error happens when the probability distribution was Q, but we guessed close to P. Okay, so now we're here. So you see, like now the good thing is that this doesn't depend on the sequence anymore. It just depends on the type. We know that the type is close to P. All right, so this approximately. So this would be basically npx, right, for every sequence that appears in the sum. So here you're getting approximately the number of sequences that appear in the sum, which is the size of this type class, times the exponential of n sum x dx log qx. Right, and then you use the approximation there, and you get, if you plug in the entropy, you get this wonderful expression. You get x to the well, n, the entropy of P, plus n sum over x dx log qx. So the second term is negative, first one is positive. There is also a way of rewriting it by, using the definition of entropy that you find right there. You can put these two sums together in one big sum. It's kind of somehow more instructive. So that's the exponential of, so the resulting sum we denote like this. Now let me write it. So this E PQ, that's sum over x dx log x minus log qx. Okay, so this quantity is a kind of fundamental quantity. You see, it's for us because it appears at the exponent, right? We got a type 2 error probability that decays like x of minus something, and that coefficient is called, well, in the classical case, it would be the Kullback-Leibler divergence, but for us, quantum people, we call this the relative entropy. So it turns out that this is exactly the Stein exponent. So the Stein exponent, you cannot do better than this. Between two probability distributions is exactly the relative entropy. Okay, this was proven by. This was an interesting story. This lemma, this was proven by Chernoff, but he attributes it to Stein, to Charles Stein, for unclear reason. Maybe Stein was the referee and asked him. But there is no published work of Stein with this. But it's there in one of his notes. So we sent somebody in some archive to fetch it, and it's there indeed. So he proved it, but never published it. The guy was really picky. So I mean, there is hope for everybody, right? Maybe everybody name something after you find in your notes. Okay, good.
But is there anything to prove? I mean, somehow.
Yeah, of course, there will be stuff to prove, right? So that.
Did you just prove it somehow?
Well, like, I mean, it doesn't take long to. That's the way you prove it. I mean, it doesn't take long to make this fully rigorous. So first of all, you have to, for example, what Ronald is saying, like you have to introduce an L1 distance here, and then okay, so this sum will contain also other types. So we contain all type classes close to P, but they all somehow have the same size. And they're not that many because they're only polynomially many types. So and the entropy is continuous. So even if you're close to the type P, the entropy is still that. So it's not hard.
Sorry, I thought maybe it's slightly different, but I thought this was called Steinov's theorem. Is that like very similar or?
Steinov's theorem for me it's something slightly different, but there are several versions. But Steinov's theorem for me it's when you have say you have a set of types.
Yeah.
And you want, well, it's basically, I mean, this calculation, yes, this would be called Steinov's theorem.
Yeah.
But this result is called Chernoff.
I see.
Chernoff's
I guess
line.
like that conclusion, but like.
Yeah. But this is basically Steinov's theorem. Yeah.
Yeah. Okay. Yeah.
So about like the stuff you have to prove. This only shows that this is a way to do it, but not the
Yes.
best way, right? So would that
Absolutely.
be
You
like
have to prove a converse. Yeah.
Oh, sure. I guess Steinov's theorem is just going to be on upper bound.
Converse is actually quite easy.
Oh, okay.
The converse is always easier because the converse is always like you say I cannot do something. And then you just have to, it's a no-go theorem. It's much easier usually. Coming up with a protocol, that's the difficult part. And we'll see the generalized quantum science lemma is exactly the same. Converse is kind of easy, and the achievability is really the nightmare. Okay, good. So far so good. But now we have to. Yes.
So we know exactly what to do when n equals 1, right? Even in the quantum case, like your measurement will just predict
Yes.
either on the positive part of rho minus sigma or the negative part of rho minus sigma. So suppose you do this n times and you output the majority bit. How bad is this test compared to the optimal?
So what you're saying is what's called symmetric hypothesis testing, in which you regard rho and sigma as equiprobable somehow. You want to minimize the total error probability. That's not the setting I'm studying here, because this is asymmetric hypothesis testing, because I'm minimizing, you see, in this quantity, I'm just fixing the type 1 error to be epsilon, so that will be large, like, I don't know, 1%, and then the other one will decay exponentially fast. If you do what you're saying, you get what's called the Chernoff exponent. So it's a quantum Chernoff exponent, which is a bit different from the relative entropy. It can be smaller. But we know how to solve that. All right. Okay, so far so good. But now I want to study a quantum setting. And you see, like, okay, so you could say, okay, I take this expression and I try to make it quantum and hope for the best. Yeah, I mean, there are several ways to do this because, of course, operators, we don't commute. Let me write two ways. One is the way that you all know, right? This one. Okay, this is fine, but what about this? This is also good. You're saying, okay, this P minus Q with the logs, it looks like a ratio. So what about I do this? And here I put, let's say this ratio. this is a perfectly valid ratio. It's a positive definite operator if sigma is invertible or positive sigma definite. I can take the log. This is perfectly valid. This also has a name. It's called the BS relative entropy for a reason. I guess many of you know this. And this is somehow so the right definition turns out to be this one, the one due to omega, which is also much simpler. But this other one, this has like fantastic properties. I will advertise this for a little bit. Has great properties. It's comes from a very elegant theory of matrix means, and it's just useless as far as we know. Yes.
At Matthias' talk, he also said that there are kind of different ways to kind of give the classical entropy, like different formulations, and then you generalize one of them to make a quantum entropy. Are there also kind of BS quantum, like von Neumann entropies?
Well, I mean, for the von Neumann entropy, if you take sigma equal to the identity, somehow everything works, right? So you get the same definition. For the entropy, somehow we seem to agree. There are no, I mean, of course, you can come up with other entropies like Rennie, but for the von Neumann limit, somehow this, we agree on the definition. There's not much else you can do. Good. All right. Well, okay. So and then okay. So the end of the story is that that's a very important result for us actually. Right here. That you can repeat this whole argument, right? Which I just stated for quantum states in the first place. We want you can compute this Stein exponent for quantum states, and it turns out to be equal to the omega one. Okay. And this was proven by Hiai and Petz in a landmark paper in 1991. Okay. Like, let me write a slightly more general version to Ogawa, who proved what is called the strong converse version of the theorem. Strong converse version of the theorem means that what I said before, proving that the limit in epsilon and the limit don't play any role. Okay, so for all sigma, for all epsilon, strictly between 0 and 1. The limit of the testing relative entropy equal to the omega. Okay. So Ogawa was like 1999, I think, something like this. All right. Okay. That's a very important result for us. Now we're going to move on to entanglement theory. Okay, so now it works. Okay, great.
So this is now the first version of the different relative entropy.
Yes, it's the first version. Yes, it's this one.
That is the right one.
It's the right one. But it's a very nice challenge to try and find an operation interpretation for the second one. It has some beautiful properties. We just don't know how to give an operation interpretation to it in terms of any task.
I thought that for many entropies, it's kind of the second one that they like more. Like for
Do they? No. For if you make everything ready here, you get what's called the geometric granular divergence, which has amazing properties. Once again, for channels, for example, it's super well behaved, but somehow it's only useful for bounds, as far as I know. It doesn't have any explicit operation interpretation. Like it's always this one, also the Rennie version, that plays a role in hypothesis testing. Because here you can also study like mixed scenarios, right? Like halfway from what Ronald is saying and what I was saying. So like you could say, okay, I have this two types of error probabilities. I want an exponential decay for both, but maybe with different coefficients. And then what comes into play is the Rennie versions of this one. Okay, right. Okay, so but why? So what's the generalized quantum Stein's lemma? This is the standard Stein's lemma, the quantum Stein's lemma. What's the generalized? Well, okay, so the generalized has to do with this setting in which you, let's say you bought a device that it's promised that it produces some bipartite entangled state rho AB, and you like that because you want to use it for your protocols, your QKD, whatever. And you press a button, it spits out the state, fantastic. But what you suspect is that okay, so this is what I mean by entanglement, right? Right, so there's a set of separable states that will denote SAB, right, with the bipartition AB. It's just a convex hull of product states. This I think you all know. Okay, and you suspect that the device is actually faulty. They're trying to cheat on you. They're trying to sell you separable states instead of entangled states. So your QKD protocol will fail miserably. And you want to decide, right? You want to decide whether the state is actually raw, so what's promised, or is some generic separable states of which you know absolutely nothing, because the adversary could try to fool you in many different ways, right?
But is it always the same, or it can be different every time?
No, it can be also different. It doesn't need to be IID. The device could have an internal memory and fool you like big time. Okay, that's the difficulty. Right, so the situation is like this. So like you have this, okay, after n uses, you have n pairs of systems, n for Alice, n for Bob, and you want to guess the state. There are two options. Either it's n copies of the same state raw, or is a generic separable state. Okay, and of course, as I was saying, the difficulty is that all the Alice systems can be entangled among them, and the Bob systems can be entangled among them. They just need to be, separately correlated between Alice and Bob. All right. So and again, we want to guess with a measurement. Let's say a global measurement. We can do anything that we like, any measurement that we want, we can implement, because we want to study the ultimate limits. People have also studied the limits where, so the situation where you can only perform a limited set of measurements. For example, those implementable with LOCC or the local ones, and then you get other results. Somehow it's easier in that setting. This is the difficult one. Okay, so again, we have this type 1 and type 2 error probabilities, which are defined as before, right? The type 1 is the state was raw, but you guessed separable. The type 2, the state was separable, you guessed raw, or raw times right. Okay, and you can define again a hypothesis testing relative entropy, which is exactly what I wrote before, except that now the type 2 error probability, this trace of sigma m, or what I wrote t, it's maximized over all separable states, because the adversary is trying to maximize your error probability. Okay, so an interesting feature of this optimization is that you can swap the mean and the max, and it's just for Neumann minimax theorem. It's just that. There is really nothing more, right? Because the function is bilinear, and all the sets are convex and compact because they're doing everything in finite dimension. Let's say you just swap them. It's kind of help. So this means that of course it doesn't help if you know. So if you can design a test that works against every separable state, you can also design a test that works simultaneously for all separable states. It's the usual minimax game theoretic interpretation, if you want. And again, we want to find the optimal Stein exponent, but now the difficulty is that the set of separable states becomes increasingly more complicated because there are all these correlations between Alice and Bob. Okay, so that's now the problem of the generalized quantum Stein's lemma is compute the Stein exponent. Define in exactly the same way. Let's say we put the limit and the liminf for precaution now, but what we're actually going to show is that they don't matter again. And okay, try to compute this. That's easier said than done. Is the problem clear?
Why is it called generalized? Why does this generalized?
Yeah, so because I have a set now of states in the second argument, even a family of sets, not a single one. Instead of an IID setting, that's why that's a quantum Stein's lemma, generalized.
So is the generalized lemma for an arbitrary convex set or specifically separable states?
I will explain that later. No, I mean the separable states is kind of the paradigmatic case, but the solution works in general under some assumptions. Right. Okay, so this right. Okay, so from the relative entropy. Okay, so let's take a detour. Let's try to make a reasonable guess as to what the Stein exponent might be, the generalized Stein exponent might be. And the way to do that is, okay, we start from the relative entropy because we know that's the right Stein exponent for the simple case. Okay, and so then we can construct a measure of entanglement out of that. It's called the relative entropy of entanglement by, say, minimizing over separable states on the second argument. So in this way, we're kind of computing the Stein exponent between a state rho and a generic separable state and minimizing over sigma. So this means that we are letting the adversary do his thing and work against us. Choose the worst separable state that gives us the lowest distance. Lowest distance means that they are more, they are less distinguishable. Okay, and since we are in quantum information theory, we always have to regularize this because we are looking at the many copy limit and there is no way out but to regularize this expression. This was a very famous entanglement measure called the regularized relative entropy of entanglement, ER infinity. And it's just defined as the limit of the 1 over n, the relative entropy of entanglement. So if you're worried about the existence of the limit, don't be, because it's the sequence ER rho tensor n turns out to be subadditive. And so there's this lemma proven by Fekete, for example, that tells you that if you have a subadditive sequence, the limit of an over n exists, and it's equal to the nth fact. So the limit is fine. Okay, that looks like a reasonable candidate for the Stein exponent, right? And in fact, you can. Oh yeah, so I should. I mean, again, the entanglement is always bipartite between all the Alices and all the Bobs. And yeah, okay, the asymptotic limit is somehow equivalent in quantum information to the thermodynamic limit in condensed matter. This is there for the physicist, make them interested. Right, okay, so what I claim is that it's actually easy to show that the regularized relative entropy of entanglement is definitely an upper bound on the Stein exponent. So why is that? Well, it's quite simple. It's kind of a side calculation we can do. Well, I mean, you see, the adversary can always, okay, so the Stein exponent, remember, rho s, like this is formally limit in epsilon, limit n. It's quite painful to write, I know, but so for example, you know, this is a minimization over separable states, right? Because I told you you can put them, you can swap this, the minimum and the maximum. So I can always upper bound this by taking any separable state, let's say in the single copy version, and doing sigma tensor n. That's going to be another separable state. Because if you have a separable state, you take many copies of it, it's still separable. So then I can compute the whole thing. Remains n, 1 over n, and here I can have ph epsilon rho tensor n, sigma tensor n. But this we know how to calculate, right? This is exactly the relative entropy. Now, if you minimize over sigma, you get exactly the relative entropy of entanglement of rho, which is clearly an upper bound on the Stein exponent. Okay, but what about the regularized relative entropy? Well, it's not difficult if you do what is called a double blocking procedure. So you take a fixed number of so you take some sigma, let's say k, in the k copy separable state set, and then you take as the ansatz for sigma n. Let's say that n is a multiple of k. You take sigma k tensor n. If n is not a multiple of k, you append some junk separable state to not pad until you get to the next multiple. It's totally fine. You don't lose much. By doing this, you can actually show that as an upper bound, you get the regularized relative entropy for entanglement. Okay, so again, the converse is not difficult. It just comes from the Ki tens, Ogawa if you want. You don't even need Ogawa, just Ki tens. Okay, so this is kind of the easy part. The difficult question is, of course, whether there is equality. Which is okay. So can we calculate the ultimate power of entanglement testing? So how well we can do entanglement testing ultimate limit. And okay, the answer is that fine, there is equality. Okay, that's the whole point. The Stein exponent is really equal to the regularized relative entropy of entanglement, which doesn't make it necessarily easier to calculate. Because you see, like on the right hand side, you still have a regularization, but the Stein exponent itself is really a nightmare, right? So this is like there is no hope of doing any calculation here. It's just too complicated. With the regularized relative entropy of entanglement, no, we know all sorts of things about the regularized relative entropy of entanglement. For example, we know how to compute it in many interesting cases. We know how to estimate it in many interesting cases. We know many analytical properties. For example, we know it's continuous. In fact, we know explicit continuity estimates. So if you have an approximation of a state, we can tell you what's the regularized relative entropy for the approximate state. And so we know so much more on the right hand side that we know of the left hand side. Okay.
On the right hand side cannot always be computed analytically.
No. Okay. Well, I mean, nothing is known about computability in general. This, in fact, these are all very interesting questions. Whether these are computable functions, even we don't know. It could be a computable. We know it's faithful also, so we can give lower bounds that are faithful, that are easy to compute. So faithful meaning that it's non-zero for every entangled state. We don't know much. For example, we don't know whether it's lower bounded by a universal function of the trace distance to separable states. This we also don't know. I mean, okay, I can talk like for an hour on this. Right, some history of the problem. Some fun because after all this technical stuff. Right, so okay, the first paper that I want to stress, it was really a pioneering paper, despite the error. It was this paper by Brandao and Plenio, the CMP 2010, where they laid out all the motivation for this generalized Stein's lemma. And okay, so then an issue was found, okay, in the original proof, because they claimed to prove it, fine, and the proof actually doesn't really work. So this was found mostly by Marco Tomamico, actually, and Gilad Gur, mostly Marco. Then we got involved for other reasons, because we tried to fix it. We could fix it in some special cases, but not very satisfactory. There was also another claimed solution later by a guy called Yamasaki and Kuroiwa in January this year. And then, okay, in 2024, we have two solutions, two claimed solutions. One by Hayashi and Yamasaki, the same guy as before, and the other one, okay, in this other paper of mine. Okay, so hopefully at least one of them is correct. I checked both. They look fine. Okay, good. Right. Okay. Yeah, sure. The memes, of course. This was a fun one. The number of proofs seemed to skyrocket for a while. It stopped. Oh, too bad. Right. Okay. So I told you why this is so important for quantum hypothesis testing. I think I have 10 minutes, right? Or five-ish. Because we started late. Okay. So, but I claim that this actually it's very important because of like it has connections to many different areas of this quantum resource theories, right? So in particular, there's a connection with the problem related to reversibility of quantum resources. Okay. Let me try to explain this because it's also important for the motivation. In fact, it was the original motivation by Brandao and Plenio. Okay, right. So everyone's favorite task, I hope, entanglement distillation, because it's extremely important, right? You get many copies of a mixed state. You want to apply local operations and classical communication, say LOCC, to turn them into some fewer copies of some very good golden unit state. For example, the golden unit of entanglement, the EBIT. And okay, so the maximum rate at which you can do this is called the distillable entanglement under LOCCs. See?
Sorry, the local operations are like analysis and Bob side, right? And then like can be global. Like
yeah, all the analysis and all the Bobs. Yes, that's fine. And then you can talk to each other on the phone. Okay.
Unlimited rounds of
unlimited rounds. Anything you can think of. We still don't know how to compute it. Anyway, so right. So it's. I mean, okay. Definition looks complicated, but it's actually very simple, right? It's the maximum rate at which you can output EBITs per state of rho. Asymptotically with some approximation error that has to go to 0. Okay. You can also look at the reverse task. So entanglement dilution, which you see you want to prepare some target state that you know it's useful for some maybe more metrological task or something, whatever you want that is not maximally entangled, because there are other useful states in general. And you want to understand how much entanglement you need. Okay, so it's just a reverse process. You run this in reverse. You use LCC operations, and you want to understand what's the minimum cost, so the minimum number of EBITs that you have to consume per copy overall produced. And so this time you want to minimize, not to maximize, because it's not a yield, it's a cost. Right. Okay, so and then there's this fantastic discovery by Bennett et al. And Brassard once, and many other people that I don't remember. Yeah, first time I gave a talk here, I think Gilles Brassard was in the audience and he scolded me because I said Bennett et al. Right, so the distillable entanglement turns out to be equal to the entanglement cost for all pure states, and it's just equal to the local entropy of entanglement. This very famous measure of entanglement is just the entropy of the reduced density matrix that turns out to govern both distillation and dilution. Great, this beautiful result. It started the whole field. And this has been interpreted, you know, like, it's more like in spirit, as something close to the second law of thermodynamics that tells you that, you know, like you can run reversible engines with some prescribed yield if you have reservoirs of different temperatures, like prescribed efficiency. And here, this tells you that you can run LOCC conversions of pure states with some prescribed efficiency in a reversible way, right? Because why reversible? Because the rate at which you can convert copies of phi into copies of psi is just a ratio of the entanglement entropies. If you want to run the reverse conversion, it's just the reverse ratio, and the product of the two is 1. Right. Okay. So somehow this reversibility really means that there is a unique measure of resource, in this case entanglement, that governs all rates of transformations of one resource into the other. And okay, so the bad news at this point is that you could hope that something like this would hold for mixed states, but this is not the case. So this was discovered by Vidal and Sirac in 2001, very nice paper, and they showed that in fact they showed an example of irreversible state. Okay, my favorite example, which is not the one they show, I think, is I think it's not that one, is the antisymmetric state. I just have to put it somewhere in any of my talks. It's just that you take 2 copies of your favorite quantum system of dimension D, and you take the normalized projector onto the antisymmetric subspace. This is very much not separable, right? It doesn't, for example, it doesn't have in the spot any product state. So it's very much not separable. That's already a proof that's not separable. So in fact, you can estimate the distillable entanglement and entanglement cost of both, and they turn out to be quite different. And so, in particular, if the local dimension of the space goes to infinity, the distillable entanglement goes to 0, like 1/d, and the entanglement cost stays fixed. It's constant. So there's an arbitrarily large gap. Right. So now, after all this bad news, Martin Planio asked himself, what does it take to restore reversibility? So what would we need to do to restore reversibility? Why does it fail exactly? And he asked this as a problem in 2005. And okay, so the main idea is to try and give Alice and Bob additional resources. Okay, so let's say that they can do something more. Let's say, for example, you give them access to some PPT bound entangled states. If you don't know what that means, it doesn't matter. Like some weak form of entanglement, you just give them for free. And sometimes this fix works. For example, for the antisymmetric state, it works. So if you use this PPT assistance, you can get the distillable entanglement equal to the cost because you lower the cost. That's out. So this fix works, and this is kind of inspired the general formulation of Planio's problem, which is, can you find a meaningful class of operations O that makes the distillable entanglement equal to the entanglement cost? This is what reversibility means, that you know, what you can get out is exactly what you put in for all states. Can that be done? Of course, you don't want trivial classes, also because everything would trivialize, right? All operations, the distillable entanglement would be infinite and the cost would be 0. That's also not good. So you want just a kind of a non-trivial class that does this. And okay, PPT operations also, so this PPT assistance doesn't work in general. So this has been proven relatively recent by Xin Wang and Miao Duan, 2017. It's a nice paper. And so the fix that they could come up with was this, introduce this kind of crazy set of operations that are called asymptotically non-entangling. Okay, so what's a non-entangling operation? A non-entangling operation is something that if you put in separable states, it spits out separable states. Okay, so anything you might want to do entanglement distillation with should not violate this rule, right? You cannot create entanglement. Okay, but then Brother and Pellier said, no, this is also not sufficient. Let's say that you can violate the rule, but just a little bit. So if you start from a separable state, you can create some entanglement, but some entanglement measure that they fix should be small. And the increase of entanglement should go to 0 asymptotically. Okay, I'm not telling you what this entanglement measure is. It's a famous one. It's a robustness of entanglement, and it's kind of the maximal one. So in some sense, if you not really, but in some vague sense, if you let that one be small, all of the other ones will be also small. And so, and one of the main results that they show, and this is actually fully correct, and it's very inspiring, I think, is that, okay, so if you do this and you define this asymptotic non-entangling operations, A and E, the cost turns out to be equal to the regularized relative entropy of entanglement. Fantastic, our old friend. That also gives some kind of half operation interpretation to that. And the distillable entanglement, you would want to say that's equal to the relative entropy, but what you can actually prove is that equal to the Stein exponent of entanglement testing. So it seems we're almost done, right? We just need to show that these two are equal. Right, so then reversibility really is also equivalent to this generalized quantity Stein's lemma. If you can prove that, you will prove that the cost is equal to the distillable entanglement under A and E for all states. That's quite nice. Right, so this kind of explains the whole connection, right? Right, so this really provides kind of a bridge from quantum hypothesis testing, quantum entanglement testing, and entanglement manipulation. Kind of what's very nice about this theorem. Right. Okay. So yeah. Okay. So the result is that they are actually equal, and I think I'll stop here. And tomorrow we do some proof ideas. Well, okay, another chance for me to thank you so much for the lunch yesterday. Really, and Chris for the work as well. I really appreciate it very much. Okay. So today you're in for some technical details, unfortunately for you. And I want to convey especially how long it took me to figure all this out. It took me really an insane amount of time. Like every step is like several months. So I think I had the first idea in after QIP Ghent. Okay, and one of the key ideas after QIP Ghent. All right. So you remember the name of the game is this hypothesis testing applied to quantum entanglement. Okay. So in practice, you have to discriminate between many copies of a state that you know, rho A B tensor n, and that's going to be an entangled state between A and B. So the set of all separable states between n Alice's on one side and n Bobs on the other side. Okay, and the fundamental quantity when you do quantum hypothesis testing is this beta epsilon quantity, which is the minimum type 2 error probability for a given error type 1 error probability threshold. So in practice, what you do is you minimize, because it's an error probability, you want to minimize it over tests that detect rho with some good probability, 1 minus epsilon, some quantifier. And then unfortunately you have this adversary that's trying to maximize your error probability. He knows your test and he's trying to maximize the error probability. So he maximizes over separable states. And okay, it's a simple application of minimax von Neumann minimax theorem to show that you can swap these two guys, min and max, and so you get this other expression. Question. Yes.
The capital S series, is it one copy or n copies?
Yeah, this is with one copy, but it's the same thing for n copies. You just need this thing to be convex. If this works for every n, then, just convexity and bilinearity of this function. Really. Okay, so since we expect this quantity to decay exponentially, we better place ourselves in the condition to in the situation where we can extract the coefficient of decay. That's why people usually define the hypothesis testing relative entropy, which is just minus log of that. It's a positive quantity. The larger the better. The more we can discriminate. And then okay, so the Stein exponent is basically defined in this with this complicated formula. Okay, so let's unpack it a bit. But okay, so we want to basically look at the asymptotic behavior of this hypothesis testing quantity of discriminating n copies of row versus separable states. We expect this to grow linearly, so we extract the coefficient by dividing by n. We take the limit because we want the worst case scenario, and then the limit epsilon going to 0 externally. And as I mentioned already, one of the results here would be that this is complete. It's too. I'm looking at the worst case scenario, but that's really not needed. In fact, this will turn out to be given by the limit of this function for every epsilon. So you don't need the limit, and you don't even need the limit for all epsilon, which is what you expect, because this quantity is kind of a very asymptotic quantity. How can it depend on the fact whether I fix epsilon to be 1% or half of 1%? It makes no sense that it would depend on that. In fact, it doesn't. And okay, so the main result that we're going to prove, which is okay, so it's this one, and it's also that this quantity equals the regularized relative entropy of entanglement overall, which I will define yesterday. It's just given by okay, so for one copy, it's simply the minimum or the infimum, doesn't matter because the quantitative logarithm continues, of the relative entropy distance from separable states. And okay, for the asymptotic limit, we just regularize that as usual. Okay, so this is kind of the natural guess because this would be the Stein exponent for two single states, and then we minimize over separable states because the adversary can choose. Right. So far with me, I hope. Great. Right. Okay. So the first realization is that this whole application, like this whole theory for separable states doesn't actually apply only to separable states. And the first step in the proof is to realize that separability is not actually needed. Entanglement is not really needed. You can formulate the problem and prove the theorem, as it turns out, in a more general setting. And this was one of the main, I think, conceptual contributions by Brandau and Plenio in their fantastic work. So they defined a general class of quantum resource theories. Okay, so you can think of that like, okay, you have a base Hilbert space, and you're going to consider sets of so-called free states, that's supposedly easy to prepare, in n copies of that quantum system for every n. Okay. So now I'm going to list some assumptions on the sets of free states that separable states satisfy, and that are very, very reasonable in general. Okay, so first of all, we want the set to be closed and convex. Okay, fine, because flipping a coin should be a free operation. We want the first set to contain a full rank state. This is important. Right, for example, maximally mixed, that should be free, or a thermal state, whatever you prefer. And okay, so we want the sets to be closed on the partial trace. So if you trace out some copies of the system, it should also be a free state. That's also very reasonable. Like throwing away systems is always like a free operation. And also close on the tensor products. And finally, close on the permutations. Okay, so these axioms are there because they're basically abstractions of the axioms that the set of separable states obey. Right? So the separable states are they form a closed and convex set. They contain a full rank state like maximally mixed. they're definitely close on the partial trace. So here I'm talking this n index is basically the number of pairs Alice Bob that are there. Okay, so when I say I trace out, let's say m is equal to 1 and trace out one system, I mean an Alice Bob system. Not, I mean, Alice and Bob are always together for this in this n index. Okay, so the base hyperspace, in other words, would be bipartite from there. And in fact, it's very difficult to think of a resource theory that doesn't obey these axioms. It's quite like magic also obeys that.
The same with the permutation. You only kind of commute,
Yes, you just swap the systems.
not between Alice and Bob, but like
No, not
among
between
the
Alice.
Alices and among the
Yes.
Bobs in the same way.
Yes. So it turns out that not all of these axioms are actually needed to prove a theorem. But anyway, they are needed definitely in my approach. I think Hayashi showed that you actually can drop some of these axioms. It's kind of interesting. But yeah, somehow there are not that many interesting examples that don't obey this. But yes.
You're implicitly assuming that classical communication between Alice and Bob is free, for instance, if they want to implement the same permutation of what's Alice's side and Bob's side.
Yes, like in this general setting, there is no Alice and Bob, right?
That's sort of the motivation from an Alice Bob
Yes.
setting.
Yes, that would be exactly. They would need classical communication.
And
Yes,
it's free, you don't charge
Yes.
rate. Okay.
it's free. Yeah, in the entanglement setting, yes. All right. Okay, so and the good thing about this list of axioms is that now we can apply the theory also to classical. Let's start from classical because it's much simpler. I can actually try to explain the proof and kind of do the proof almost. Okay, so what does it mean? Like, okay, so let's say you have a finite alphabet instead of a finite dimensional hyperspace, and you have Fn will be a set of free probability distributions on n copies of the alphabet. Okay. And then you assume they run Laplacian axioms. It's perfectly fine, right? Tracing away means discarding one symbol, and so on. And you can define exactly the same things. You can talk about the Stein exponent, okay, same formula, exactly same formula with a set of free states or free probability distributions. And you can also define a regularized relative entropy of resource, which would be exactly this, the regularized relative entropy of entanglement, right? And same formula. And now you can ask yourself, okay, is this really true? And okay, so like the statement is exactly the same as before. You see, like the limit doesn't depend on epsilon. Okay, in particular, the Stein exponent is equal to, if you take the limit epsilon going to 0, you get that the Stein, which does nothing. You get that the Stein exponent is the regularized relative entropy of resource. Okay. Questions so far? I think it's pretty okay. Good. Right. Okay. So I need to. Okay. So we are not going to solve the problem in that form. So we need a transformation first. And for the transformation, I need to introduce this max relative entropy, which is very cute quantity. This was introduced by Nilanjana data in 2009. Okay. So you see how it's defined. So basically, you want to dominate rho with a multiple of sigma, and you ask for the smallest coefficient that does that. And it's very intuitive, right? So this would be, if this were classical probability distributions, it would be the maximum ratio. Okay, but this quantity is a max relative entropy, so in general, it's much larger than the relative entropy, so it's not very useful for us. We have to try to kick it a bit so that it becomes closer to the relative entropy. And there's one way to do this, very famous one that's kind of important in cryptography, which is, yeah, okay, for this, I mean, this was a semi-definite. The way to do this is smoothing. So smoothing means I now let the first argument vary a bit so as to minimize this quantity. Remember, it's large. We want to make it closer to the relative entropy. We want to minimize it. Okay. And there's this fantastic fact of life that you can turn the hypothesis testing relative entropy into the max relative entropy if you are willing to swap epsilon for 1 minus epsilon. Okay, I'm being very imprecise there, but the exact relation is like this. So the D max 1 minus epsilon square root this actually holds for all states. This holds for all and for all states. And I assume that eta is between 0 and 1 minus epsilon. Okay, so I'm cheating a bit because you see like you get a 1 minus epsilon on the right hand side minus a small remainder, and the square root 1 minus epsilon on the left hand side. But it doesn't matter because yes.
Is there a specific norm you choose here, or does it not
Oh
matter?
yeah. The smoothing is trace norm.
Okay.
Yes. You can also do purified distance, and then it's actually even better. You can, but it's fine. Okay.
Question?
Yes.
So smoothing with 1 minus epsilon means that the row prime that you allow could be super far away from
Yes,
the row.
but not orthogonal. Epsilon is between 0 and 1.
I see, I guess.
Since we're doing the asymptotic limit, this will kind of not matter.
Okay.
But this is the main point. Right, okay, so like you see, like we're trying to prove something for every epsilon. So swapping epsilon for 1 minus epsilon doesn't matter for us, or square root of 1 minus epsilon doesn't really matter for us. If you can prove for all epsilon for d max, you can also prove it for all epsilon for dh. So if you're surprised by this, I was also surprised, very surprised. It's I call this a weak strong converse duality. So you relate epsilon in the when epsilon is small to epsilon close to 1. It's like weak converse versus strong converse. But okay, so in essence, this is just an application of, so in the classical case, this is just an application of the Neyman-Pearson lemma. I learned that Neyman was Polish, not Neyman.
This 1 minus epsilon thing is a bit confusing because then you're minimizing over almost the entire set.
Yes, absolutely, yes.
So
So
that seems like a very weak bound, right?
it seems a very weak bound, right? But we are going to
Because
the
epsilon goes to 0.
eventually, but after n. So indeed, we can assume that epsilon is fixed. So, but you see, like if you are not completely orthogonal to rho tensor n for large n, and rho is very entangled, you are also very entangled.
So even being epsilon, like
Even if you are like 0.99 close to that, and but in a fixed way for all n, then you're also very entangled. That's exactly what this theorem is saying.
Because it still adds up.
This is equivalent to the Stein's lemma, to the generalized Stein's lemma. If you prove this, you're done.
Oh, okay.
That's
Not so easy,
that's
yeah.
exactly the difficult part. Okay, but somehow it has to work. No way it's not working. Okay. Right. I mean, I said okay. So I was saying like this is equivalent essentially to the Neyman-Pearson lemma, right? The Neyman-Pearson lemma tells you that if you want to do hypothesis testing, this is the same as looking at the maximum likelihood ratio, right? Like you should look at tests that are like this: the x in the alphabet such that p of x smaller than tq of x. This would be your test, optimal test for Neyman-Pearson. So you see like a D max just popped up. All right. Okay, so and as I was saying, if we prove the theorem for DH, we prove it also for D max. They are perfectly equivalent, okay? Because of this epsilon 1 minus epsilon. Great. So I'm gonna prove it for D max. And we prove it by contradiction. Okay. Right. So let's look at this horrible function. Let me define this function. I don't know, f plus minus of epsilon, let's say, just because I don't want to rewrite them. Let's say that this is limit, no, sorry, without limit. Lim, let's say sup or if we want to be super careful of this quantity. When rho tensor n or p tensor n, and then our free states. There's a function of epsilon, right? Function of epsilon, so there are two functions, f plus and f minus. Of course, f plus is larger because it's a lim sup. And they're also decreasing in epsilon. Because you see that epsilon is a smoothing parameter. The larger epsilon, the more room you have to smooth. So the bigger the ball, so you're minimizing, so it's going to be lower. So these functions are decreasing in epsilon. Right. Okay, so and what we want to prove is that they're actually constant. So for the limit, they're both decreasing, yes, because every term is decreasing. Both of them are decreasing. So we want to prove that they actually don't depend on epsilon. So we're gonna prove, see like there. We are just going to prove that essentially. So we need to prove just f plus of let's say 0 for the limit epsilon going to 0, smaller and this. And then F minus of any epsilon larger than this. If we prove this, we're done. The functions are decreasing. We just need to show that they actually don't decrease. Okay, so and it turns out that the first fact is actually very easy. Okay, the limit epsilon going to 0 of that function, that's equal to the, let's see, it is PQ and rho F, whatever, typo. But both in the classical and the quantum case, this is very easy. And why is that? It's basically the converse statement that we showed yesterday. So here you have something like this. So you take some ansatz sigma for your free state at the 1 copy level. You repeat it n times. That's going to give you an upper bound on this. D max epsilon rho tensor n sigma tensor n. And let me write it down. So let's see, F plus epsilon, that's smaller than lim sub n 1 n d max. That's basically the reasoning we did yesterday, but okay, for those of you here. Okay, this works for every sigma in the first set, the first level of the set, because sigma tensor n will be again a free state, so I can plug it here. And this is, we know how to compute this one, because this is just the standard quantum Stein's lemma, just IID states. That's perfectly well known. Okay, this is a D max epsilon instead of DH epsilon, but we know that doesn't matter. You can always turn one into the other. So this is just the relative entropy between rho and sigma. This is basically kind of the Ogawa strengthening of the standard quantum Stein's lemma. Strong converse. Okay, so then you can take the limit epsilon going to 0, and you get the relative entropy, and you can also regularize it with this double blocking procedure that I showed you yesterday. So you can take, instead of sigma at the 1 copy level, you take sigma at the k copy level, and then you tensorize that, right? So you get some sigma k tensor, well, n over k, integer part, throw away a bit, and then you get the relative entropy. In this way, you get the relative entropy. You get this bound, rho tensor k, sigma k. Then after that, you can take the limit k. Okay, so this upper bound is actually very easy. This is basically done. Okay.
Wait, sorry.
Yes.
Why did we do this double blocking procedure as well? Did we already derive?
Because in general, this thing minimized over sigma is not the right thing we want, right?
Oh, that's
The
right.
right thing we want is this regularized expression.
That's right. Yes.
So you need to, after that, you need to do this double blocking procedure.
I see. So it's like we got E R rho, but we wanted the E R infinity. Yeah.
But that's fine. That's fine, because this limit in n kind of absorbs everything.
Yeah.
Okay. So the key part is to prove this, the second statement. So the function actually doesn't decrease. You have this function, and it's basically what you guys were saying. So like we want to show that for a finite epsilon, this smoothing doesn't do anything. Although you might be very close to 1, but if you're close to 1 in a fixed way, it doesn't do anything. Okay. Good. So this is the converse. The problem is achievability, as usual. So let's assume that achievability doesn't hold. Okay, so let's say that this function, this f minus of some epsilon now is a fixed number between 0 and 1, 0.99 if you want. It's smaller than lambda, strictly smaller than the regularized relative entropy. Let's draw a contradiction from that. Okay, so let's unpack this. Now the advantage of working with Dmax is that Dmax is a minimum. So if a minimum is smaller than something, now I can construct stuff, right? I can say, okay, there exists a Pn that's a smoothing of P tensor n. So it's epsilon closing trace distance, and a Qn that's free, such that Pn is upper bounded by 2n lambda Qn. It's just the unpacking of the statement. So see, like this is, it's kind of okay. So you have a state that's not orthogonal to P tensor n, that's dominated by a free state. And okay, by axiom 5, you can assume all of this probability distributions to be permutationally symmetric. So take the same value on all segments, okay?
So I guess you're also using convexity.
Just convexity.
Yeah.
There's a Pn that's already equivalent to and lambda is just the
Lambda is that,
positivity thing. So
lambda is that number.
yeah, it's like they're like
Yeah, and true wise,
That positivity
yeah,
thing.
on every sequence they are exactly this one. And true wise. Okay, so now since everything depends only on types, remember will be a slide on types, but now we can look at this in type space. Okay, so right. So you remember what the type is, right? The type of a sequence is just the empirical probability distribution, right? Number of times that any symbol appears in the sequence divided by n. Good. And okay, so we know also that P tensor n is concentrated around P by the law of large numbers. And okay, the other important fact to keep in mind is that there are exponentially many sequences, but only polynomially many types. Yeah, very fundamental fact. And okay, so let's look at the sequences in type space. That will let us understand things. Okay, so that's a pictorial drawing, I guess. So you see the yellow thing is P tensor n represented in type space. Okay, so on the x-axis there are the types. So for example, if your alphabet is binary, this would be a number between 0 and the size of the alphabet, would be the number of ones in the sequence. Okay, if the alphabet is not binary, you will have larger space, but still. Then P tensor n will be concentrated around type P. See, all of the weight of types are close to P. And okay, so the only thing we know about Pn is that it's not orthogonal. Okay, so it's epsilon away. So it will have a shape like a crazy shape like this. But what we know is that it needs to have some weight on this typical set of types. Because otherwise it would be orthogonal. Like P tensor n is concentrated there, Pn needs to have some weight there. Good. So now the main idea, if you want, of the proof is a procedure that I call blurring. So what's blurring? Well, it's a quantum channel, or in this case, a stochastic map. So it's an operation that I do. What do I do to my probability distribution over n symbols? I take this Q naught. Q naught is the full support free probability distribution in the first level. So basically, every symbol appears with some non-zero probability.
adding the maximum mixed.
Sorry?
You're adding the maximum mixed.
Essentially, you're adding copies of the maximum mixed state, for example. You add m of them, and you should think of m as a small fraction of n. Then you symmetrize, you shuffle all the symbols, and then you throw away m symbols, so as to go back to n symbols. Okay, it's a very simple procedure. It's clearly a quantum channel. If it's clearly quantum generalizable, it's clearly a channel. Everything works. All right, random permutation, discard m symbols. Right, and the key thing is that any sequence of symbols might be added into the input sequence because Q naught is full support. And the other thing to observe is that by the axioms, this maps free states to free states because everything's free. Great. Okay, so what does this do? Well, okay, so we can turn all of this. You see, like on the top left, we have the inequalities that we got ourselves. And now we can apply the blurring map to everything. And since it's a channel, it will preserve everything, will preserve positivity. Right? So we got this P tilde n, which is the blurred version of Pn. Right? Pn is this crazy red probability distribution. We blur it now. And we know that's going to be upper bounded by 2n lambda, the blurred version of Qn, right? Because that's just the blurring map applied to the inequality in the top left. Okay, but what does the P tilde n, the blurred version of Pn, look like? Well, you see, that's what blurring does, right? Blurring adds some noise to the probability distribution, so it kind of blurs it, right? So it lets basically the type, so the weight on every type gets, you know, like it kind of leaks over neighboring types. That's what it does.
Is it clear what this map does in sort of type space?
No, you have to work it out, but it's very simple. It's just combinatorics at this classical level. So it's just so once you understand that this is the right thing to do, it's not one page.
Sort of convolution with a Gaussian.
Yeah, I mean, like, yeah, I mean, like, okay, like to analyze it, you need this hypergeometric distribution.
Okay.
But you're just shuffling. You're just shuffling stuff.
Everything's Gaussians, but.
No, but exactly. Eventually, you use these kind of things. Yeah, eventually you use that. Yeah.
Because if I sort of only blur, I would end up with a
No, it's not a Gaussian
Yes.
type space.
This will become relevant at the end.
Okay.
Yeah.
There's also like a concept in like Boolean function analysis or other generalizations thereof where you do like a noise operator, which feels kind of similar to what you're doing. It's very similar. Basically, you look at all the bits and you IID, like flip them with, basically you can imagine it as applying a BS, like a binary symmetric channel to all the bits.
Oh, yeah, yeah.
And it's like the way you have like some sort of function probability distribution, which may be kind of.
I think that the spirit is there, yeah.
Yeah.
Also, there are many ways of doing this blurring.
Yeah,
I'm
yeah.
showing you one way, but there are other ways.
Yeah, it's kind of.
Oh yeah, why can't you do it with sort of a binary symmetric type channel where you look at your string and then you look at your original sequence and then you sort of shuffle them a little bit?
I think that's also doable.
Yeah.
You have to do something that makes the analysis easier.
Yeah, but
And
this
this
is
was the
just
best
a
solution so far.
structurally nice thing. Okay, cool.
But it's by no means the only way. And maybe there are easy ways that I haven't seen. But yeah, this would be a
strong
one
notion
way.
of smoothing
This
that.
would be a thing one. But you need to have something that works also in a quantum case.
Yeah.
But okay, maybe.
I mean, this noise operator is popular because it has like hypercontractivity results. So if you take a function, because not only is it smoother in like the same norm, but it becomes smoother even a stricter norm in some sense.
yeah.
So you can like kind of bootstrap it in some sense.
Yeah. But okay, so here we did something slightly different, but
Yeah. So it might be a different property you need. So
So this noise operator behaves extremely nicely in Fourier space.
yeah, that's the other reason it's popular. Yeah.
Which is sort of a type
Yes.
space.
So it's because of the convolution. Yeah, because it's a convolution, so it becomes a product. Yeah.
yes, but okay. So you're saying in Fourier space maybe it would to analyze.
The Fourier functions are eigenvectors of the noise operator. Fourier instance.
Okay, but so what? Okay, but
Yeah, but
so here we have a discrete alphabet, so we want to do discrete Fourier transform.
Yeah.
But it might not be prime, but that's not a problem. Okay. Yeah. Okay. So that's something to look at. Yeah, that might be good. Okay. So I tell you what we don't care about. We don't care about what happens here in this side. We care about what happens here. What happens there is that now, because of this spillover thing, basically P tilde n, so the blurred probability distribution fills this whole typical subspace with a constant weight. Okay, not really uniformly, but at least uniformly. So it has filled it to some level. And if you're worried by this, well, remember that there are only polynomially many types. So you can spread some small weight into all of this space by paying only a polynomial factor, essentially.
It covers most of the types or all of them?
No, it won't cover the tails of p-tensor.
Yeah.
It will only cover the typical subspace.
Okay, yeah,
If
sorry,
you add
yes,
some
good,
enough
yeah.
noise, like small noise. But it won't cover the tails. So
Yeah,
we
I
still have to cut off the tails.
Yeah, I guess making that precise is difficult.
Yeah, in the classical case, it's not so difficult, but yeah, you have to work a bit. 2 pages maximum.
Oh, okay.
Right. Okay. So what I was saying right now is that okay, we don't cover the whole set of types of p-tensor n, so we still need to cut off the tails. So I introduce some eta parameter that allows me to cut off the tails. So I get this p prime n. And the standard notation is a bit. But okay, so this p prime n is just the cut version. You know.
Yeah, you cut off the tails. The pictures are clear.
Great. So this p prime n is dominated by this p tilde up to some small exponential factor. In fact, probably even polynomial factor, but I didn't show it. Okay, so you pay a small price, 2 to the n delta prime very small, and you dominate that. Now we are basically done. Because you see, like p prime is dominated by p tilde, but p tilde is dominated by the blurred version of qn, by what we said before. Yeah. So we get that p prime n is dominated by a free probability distribution with a coefficient that's basically n lambda, 2 to the n lambda. And this implies, like, if you rewind back the thing, you get that the d eta max of p tensor n is smaller than n lambda plus delta prime. Now I see the advantage now is we have turned an epsilon that was far away from 0 to an eta that's very close to 0. Now again we know what's happened because we turn this f plus epsilon or f minus epsilon, I guess, into f minus of 0 or f plus of 0. Same. Okay, so this statement is really what I call this classical blurring lemma. It's easy give names. And so this implies if you divide by n, take all limits, it implies this. So that this function for eta, okay, forget about the plus and minus because that doesn't matter. So, but the function for this f of eta is smaller than lambda. But then we know that this one is in the limit eta going to 0. That's exactly what we're looking for. So it cannot go down. So with this blurring technique, you turn some epsilon into some small eta, large epsilon to small eta.
So, I mean, this may be a minor detail, but shouldn't it be like lambda plus delta is the upper bound you prove? And I guess if delta is small enough.
Yeah, but exactly. But delta will depend on eta and that will also go to 0.
That also
I haven't
goes to
written down exactly what delta
Yeah,
prime
I
is,
see.
but it's a small number that goes to 0.
Yeah, of course, yeah. So it does disappear in the limit as well. Yeah.
All right. Okay, so then we are done. So we can try to replicate this now for the quantum. Okay, so that's a blurring lemma. So, it's basically what I said. Doesn't look too bad. The analysis is very simple. Maybe it can be made even simpler. Be surprised. Okay. So I have now, I guess, 20 minutes to tell you about the quantum version. So that like structurally, yes.
Can you give like a high level recap of like how you got the contradiction?
Yeah, I got a contradiction because I termed remember, so we started with a large epsilon, and then I like this function computed for large epsilon, and then I showed you that this is basically equivalent to the function computed for a small eta. But we know that in the limit, when epsilon or eta goes to 0, you have to get something that's yeah, actually I didn't show, but this works with equality. This I should have said. This actually works with equality. Like of details on my side. So this. Yeah, I mean this is actually works with equality.
Well, yes, you can prove that if it's strictly smaller, it's actually equal.
Yes. So this function, this mysterious function that we want to analyze, it has the right limit for 0. So it's equal to the regularized relative entropy for 0. And that's kind of simple to show. I showed you the converse, which is the statement that I had before, but also the other way is very easy, comes from something called asymptotic continuity. Essentially, I mean, this function is at Emax, right? So the max relative entropy is always larger than the relative entropy. So it's not difficult from that to show that you cannot actually. So if you go epsilon going to 0, that means you're close to row tensor n, and the relative entropy cannot change much. The max relative entropy is only going to get bigger. So you cannot go above that, but it has to be at least that. So for 0, it's kind of very fast.
Yes. Also, a property you need that I don't think you've mentioned is that f needs to be continuous in epsilon for this contradiction to work. Or?
Yes, you can show that this is continuous at 0. This you can show explicitly. But you don't have any control for larger epsilon. But for 0, and it's true.
So like if it's at a large epsilon, it's like it has the wrong value, then you can show it a small value has the wrong value, and then using the limit and continuity, that's a contradiction.
Yes.
Okay.
Cool. Is it a bit better like this?
Yeah, a bit. I mean, I see that it formally works, but somehow intuitively.
Well, I mean, like in the limit epsilon going to 0, it's kind of very easy because you're very close to row tensor n. You cannot be almost orthogonal. No? You have to be very close. So like there are some standard continuity techniques, like by Andreas came up with this. I think Alitsky Fanes and Donald also for the relative entropy. That show you that the relative entropy is well behaved. It's continuous. So that, for example, the relative entropy of entanglement is continuous. It's actually asymptotically continuous.
Why did you have to do all this with the max entropy instead of just the regular one to start with? Because you made this sort of this switch, and then you can prove like things here. So
yes.
Is it because like this like equation like it's just smaller than small squared? It's just much easier to work with then.
Yeah, with the Dmax, I don't know. Yeah, it's kind of easier because it's a minimum instead of a maximum.
You can sort of operationalize the contradiction.
Yeah, you can. Yeah, somehow.
This
Yes.
must happen.
Yes, but there are also ideas to work directly with the age. Okay, more or less on board. Okay, so like structurally, the quantum proof works in the same way. Okay, so there's a blurring step, and it's like everything works in the same way. But the point is that the blurring step now it's way more difficult to prove. Okay, so the blurring map, you can do exactly the same thing. You can append your full rank free state and copies of it. You can symmetrize, apply a random permutation, then freeze out m copies. This just works the same way, perfectly fine. And so this is the basically the quantum blurring lemma, the version of the quantum version of the lemma that I showed you before. This is actually not what I prove. It's an informal and wrong version of what I proved, but it conveys the main idea. So okay, so we have a sequence rho n that's not orthogonal to rho tensor n, so it has to stay at distance epsilon. That's not 1. And now what I'm saying is that if I apply the blurring map to rho n, I dominate rho tensor n approximately. So what does that mean? Well, it means that if I do rho tensor n minus that, and I compute the positive part, the trace goes to 0.
Oh, yeah, the plus is like projection onto the.
Yes, it's the positive part. Okay, so let me really elaborate a bit on this.
Asymptotically,
Yes.
rho n is smaller in this
exactly right.
P sense than the.
Yeah, exactly.
Okay,
So-
very good, yeah.
Yeah, so x plus for me is
Complicated way of saying that.
absolutely, absolutely. So the trace of x plus for me is just the sum over the eigenvalues of the spectrum of x of the maximum between lambda and 0. Okay, sum of the positive eigenvalues essentially. And now what I'm saying is that okay, so basically if you define delta to be the positive part of this operator, and delta prime, and this again a small thing, small parameter. This is the positive part of the operator. So now what you get is that rho tensor n smaller than this. Plus this delta n.
Is there a reason with this particular notion of sort of approximate positivity?
So it turns out that so there is a lemma proved by Nilangelo Datta and Renato Renna that tells you that if you have something like this, coefficient sigma plus delta, delta positive, and trace of delta smaller than some delta, very small, then you can find a rho prime, which is, now I forget exactly, but like close to rho, such that rho prime is smaller than 2 to the lambda sigma.
Oh, there's a stability result.
There's a stability result.
Yes, if you're approximately dominating, you're close to an exact.
Yes, yeah, exactly. Because you have to pay 1 minus delta, but it's fine. It's a very cute result. It's basically Renato Renna's, I think. It's kind of nice, right? Yeah, exactly. If you dominate approximately, then you're close to a state that's dominated exactly. Nice. It's not that easy to show.
Is it just a consequence of the fact that eigenvalues are sort of continuous?
Not really, because you need operator domination, right? So these two guys might not be like, okay, if they commute this, everything is easy, but in general, this needs proving. That's why, I mean, this notion of approximate domination that I'm using is the same as, being close to a state that's exactly dominated. Okay, so basically what I'm showing is that, okay, so this trace of this operator goes to 0. So you are in this approximate domination setting. And then you see now that the final statement will be exactly using this lemma, that I can erase this delta n, and I can approximate. Instead, I can use an approximation here at this rho tensor n level.
I guess the tricky part is doing it without incurring a dimensional factor in the
Absolutely.
wiggly parts.
Exactly. This works for any dimension without incurring any penalty. Okay. So now that kind of the second main idea took me really like months, like a year to figure out is how to prove this quantumly. And okay, I came up with a hack, but I don't think it's the best way of doing it. I think it's very much not the best way, but it's somehow what I could come up with. Yes, Ron.
Is there any relation with the Finetti theorems?
Ah, yes, you would think so, right? But somehow I couldn't do it. I was yeah, of course this is gonna be definitive, but somehow it's not. It's well, first of all, you would need some definitive reduction, right? You know this thing with operator inequalities. But somehow I couldn't make it work. Because you need a constrained definitive reduction. Constrained with definitive. So like in which you, let's say, you have a big what you would like is that you have a big separable state, permutation symmetric, you upper bounded with a convex combination of any separable states.
Yeah, you reduce to the n equals 1 case.
Yes, but that's not true in general. For example, for separable states. So yeah,
You need it to be approximately.
you need
true
you need
with the
also to
limits,
include
yeah.
approximately separable states, since these are not separable but close to the separable set, but then things become very messy. Yeah, there's a nice paper by Andreas Winter and Cecilia Massian called flexible definitive reductions, and they do these kind of things. But yeah, essentially, kind of the take-home message is that this is incompatible with free states. We're remaining inside a set of free states. Okay. Right. So but then, okay, the main thing is how to prove this quantum blurring lemma. Okay. And the way I could do it, the only way I could do it is by this crazy proof strategy. Okay. So first step is purification. So let's say you purify everything. You assume that rho is a pure state, and rho n is pure and permutationally symmetric. You can do all this because the blurring map respects this permutational symmetry. Okay, so but by data processing inequality, you get something like what's there on the right hand side. So rho has become state 0, so some pure state that I call 0. And now you got this phi n that's any permutationally symmetric pure state. Okay, and you've got this blurring map. Now this blurring map, the way I defined it before, it actually projects you out also of the fully symmetric subspace. But now I modify the definition, I project down to the fully symmetric subspace. So I make sure that I stay inside there again. Yeah, but symmetrizing means that you're diagonal in the Schur-Weil thing, right? But no, I want to have components only in the fully symmetric subspace. So I just project down there and neglect everything else. Yeah. It turns out this is fine. Doesn't matter anyway. Because the first state is anyway in the permutationally symmetric subspace. So whatever is on any other representation of the symmetric group, it just doesn't contribute to the positive part. It's just it's a negative thing on that block. It just gets killed by the positive part. Okay. Right. So now the problem is, what does this projected down blurring map that stays inside this full symmetric subspace look like? Yeah, that's what I don't know how to analyze effectively. So now the only way I can do this, and it's a bit ridiculous, but it's also somehow beautiful to me, is okay, symmetric space I don't understand. So what do? I lift everything up to a bosonic space. Sure. Why not? I embed everything into an infinite dimensional space. That's sure. Why not? And okay, I think you all know how this embedding works. And if you want kind of explicit, let's say that you take the case where you let's say that we are in a single qubit, right? So now we want to embed the fully symmetric subspace of n copies into a bosonic space. So a bosonic space, if you don't care about L2 functions, like some people do care, but if you don't care about that, if you are a discrete mathematician, you can think of this as the sequence of complex numbers that are L2, right? Some squares, finite. Okay, so how does this embedding work? Well, okay, so the fully zero vector, right? 0 tensor n, of course, it gets mapped to the vacuum. The first element in the sequence. Right? This would be like the sequence, like 1, 0, all the way to infinity, right? So, okay, so a basis, like this, the standard basis of the fully symmetric subspace, which is like, okay, so here we put square root n, and then there would be, you have 1, 0, 0, plus all the permutations, so the 1 can go in any place. And we interpret this as the state having one excitation anywhere. And we map this to 1. And we continue this way, right? Like, okay, so here you will have the second state would be like, okay, n choose 2 inverse square root. And then here you have 1, 1, 0, 0, plus all the permutations, right? So like 1, 0, 1. And this gets mapped to 2. Okay, there's a perfectly valid embedding. I can do this, and now I can look at everything in the bosonic space. Okay, why is that a good idea? Well, okay, because in the bosonic space I know much more somehow, and it turns out that the blurring map has a nice limit in the bosonic space, in a very precise sense.
So sorry, but like you have qubits, so I guess you will just make some convention how it's embedded.
Yeah, if you have qubits in general, then here you can have several types of excitations, right? You can have excitation 1, excitation 2. And so then what happens is that here you have to record how many of each type of excitation you have. So you get this thing, tensor d minus 1. That's it.
Because it's already in dimensions.
No, it's infinite dimensional, so it's fine. It's fine. Then you get what's called a multi-mode bosonic system.
Yeah, which is perfectly
Which is fine.
fine object.
Which is fine. Yeah, once you solve the qubit case, you're basically done somehow. Yeah, okay, so that kind of the key insight that took me a while to realize is that this blurring map, you see, what does the blurring map do? Well, you append the vacuum, right? And then you do some symmetrization, and then there's some small probability of leaking out excitations into the vacuum. Well, that's what people in bosonic non-quantum information call the pure loss channel. Pure loss channel is a very well understood quantum channel, and it turns out that in some sense, some precise sense, the limit of the blurring map in this bosonic space is equivalent to this to a pure loss channel.
So when you say limit, you mean limit with respect to n?
Yeah, limit with respect to n.
Okay. Okay, so you're looking at higher and higher sim n.
I am, yes. It's kind of, but I mean, like making this very precise,
Yeah.
this takes like 18 pages in the paper.
Okay.
It's really kind of the difficult part, I would say.
Yeah, you're carrying
Which
the
is
lead here.
The only non-trivial part.
which limit are you using?
The limit n going to infinity.
Yeah, but which is the precise?
Yeah, okay, so yeah, that's the other thing. You need to be careful because you want yeah, so the weak star topology turns out to be. Yeah, because like you need the space that's infinite dimensional to be compact in some sense because you want to extract subsequences. And okay, there are topologies that do that, like this weak star topology that makes this infinite dimensional spaces, the unit balls compact somehow. All right. So now you see like this delta will be something like the transmissivity of the, well, 1 minus delta, I guess, will be the transmissivity, because delta will be the probability of leaking out excitations into the environment, right? Okay, so then the final part of the proof is that after I take this limit, I use tools from well, actually complex analysis to analyze this pure loss channel. But that's much easier because we, like for bosonic systems, we have all sort of tools that are available in the continuous variable case, like characteristic functions and Wigner functions, name it. Using these tools, it's about Bargman, Sagal, transform, also that's not one. Using these tools, it's not difficult to solve the problem on the right hand, to show that the right hand side goes to 0 once you have left an everything bosonic subspace.
The hard part is taking the limit.
Yeah, that's the painful part. You have to make sure that everything goes where it should go. That's really the only not real puzzle data to address this gap. All right.
Very strict definition of non-trivial.
Yeah, no, but this was the. I think it's kind of beautiful that, well, to me at least, that you can turn this generalized Stein's lemma, which has nothing to do with continuous variable, to a pure loss function problem. Yeah, quite unbelievable to me, and yeah. But yeah, some of the.
Yeah, and then once you have a pure loss channel, you can just sort of do